In this video, we're going to be solving for optimization problems using derivatives. So let's show you how to set this up. So a farmer has 240 meters of fencing to enclose a rectangular field and divide it into two equal parts. So a representation of this fencing just looks like this, where each line is some fence, and these are individual places where maybe a cow can reside or something like that. Like there's a cow here, there's a cow here, cows with two legs. And they're parallel to one of the sides. What are the dimensions that maximize the total area? So, first things first, in order to maximize the total area, well, of course we need a area function. So the area function for this is length times width, right? The length of the entire fence times a width. And the thing about this function is that we have another function to this, which is our constraint, which is the limited amount of fencing that the person has. So 240 meters times, well, there's two length sides, right? There's this side of the length and this side of the length. So we have 2L plus 3 widths of fencing. So we have 3W. And these two equations you can solve and maximize the total area by, of course, using critical points and like. But first things first, how to use this? Well, we need to isolate some variable. Isolate W or L, doesn't matter. I'm just going to choose L for this example. So when we isolate L, you get 240 minus 3W over 2, and this is equal to L. Therefore, we can replace this into this area function. Get area times is equal to 240 minus 3W over 2 times W. Okay? All I did here was replace and substitute L into the area function. Now that we have this, we can take the derivative of area with respect to W. So, the reason why we substituted L here was because we can't, at least with the current knowledge you guys have, you can't take the derivative of a function that has two variables. In calculus 3 you will learn that. But for this, you cannot take the derivative of a function with L and W, so you need to set L in terms of W in order to take this derivative so that you have just one variable, W, in your function. So if I just make this a little more simple so that you can use power rule for this, we get 120W minus 3 over 2W squared. Now all we need to do is take the derivative of A with respect to W, and then you should get, let's write A prime, you should get 120 minus 3W. Well, the thing about optimization is that you need to find the critical points of your function. All right? With optimization, you need to find local maxes and local mins, or absolute maxes and absolute mins. So you can use your knowledge of critical points in the second derivative test to find the maxes and mins. Let's go ahead and find the max. Let's go ahead and find some max. So the only time when your first derivative of area is equal to 0 is when W is equal to 40. Okay, this is good. Well, when W is equal to 40, that's the only, I guess, the only critical point. So you can kind of already safely assume that this is the local max, but let's be safe and take the second derivative. So the second derivative of your area is negative 3W. And when you plug in 40, your critical point in this case, you get negative 120. And since you get a negative number for your second derivative test states that this is a max, a local max. Therefore, when the width is equal to 40, we maximize the total area. But still, we need to find the length, right? So, in order to find the length, we can use this formula here. So, 240 is equal to 2 times the length plus 3 times the width. But we already solved for the width. So, the width is 40. 40 times 3 is 120. And doing a little bit of algebra, we get that the length is equal to 60 off of this equation here. So the length and the width of this farmer's fencing is 60 meters for the length and 40 meters for the width. If you've made it this far in the video, consider subscribing and liking the video. Yes, I'm a sellout. Yes, I want more subscribers, and I appreciate all of you guys that do subscribe. I also appreciate the people that aren't subscribed. Kind of. Just kidding. But let's do this problem. So we found the dimensions of an open-topped rectangular box with a square base and a volume of 32 centimeters cubed that minimizes the surface area. So we want to minimize the surface area. We want to find some local min in the surface area formula. So I were to draw the box. Kind of looks like this. Okay, I got to stop clicking Control X. And this box is drawn like so. All right. Okay, that's a very bad line, but here, let's draw it with dotted line. Let's draw a dotted line. It's slanted. Okay, I'll just leave that be. But this is our box, and since this is a open top rectangular box, so it's open top, I'm gonna shade the base, but the top is open and has a square base. That means the length and the width are the same, right? So we'll just use one variable, which is represented as width, and the height of the box is h. So we want to minimize the surface area. We already have some constraint, which is the volume. So we can write the volume formula, which is height times width squared in this case. And we also need to write the surface area formula, S, which is your width squared, so that's your area of the base, plus your 4 times height times width. And the reason why I put 4 is because height times width represents the area of all 4 sides of this rectangular prism. All 4 height times width sides. So let's go ahead and isolate some variable. Pick one, h, height or width, doesn't matter. We can isolate using this formula. So if we wanted to isolate height looks easier to isolate. We can do 32,000 divided by width squared is equal to height. And then we can substitute height into this equation here, into surface area equation. So your surface area equation is your width squared plus 4 times 32,000 over width squared times your width. If I wanted to simplify this further, we get width squared plus, what's 32 times 4? All right, I got to pull my calculator for this. 32,000 times 4 is 128,000. So you get 128,000 over width. And all I did was cancel out these values. So now that we have the function for the surface area, we can take the derivative of the surface area with respect to width now. So S prime, the derivative of this function, is 2 times the width plus, actually minus 128,000 over width squared. So now that we have the derivative of your surface area, we can do the optimization. Set the first derivative equal to 0, and we get 2 times width minus 128,000 over width squared is equal to 0. So we need to isolate width in order to tell. We need to set width equal to 0. So let's go ahead and write a function for this. Width is equal to 128,000 over width squared. I just moved this term onto the 0 side. And then multiply width onto both sides to cancel out the width in the denominator here. To get width cubed is equal to 128,000. And then you get width cubed is equal to 64,000 once I divide 2 on both sides. And in the end, you should get that the width, after you cube root both sides, you should get that the width is equal to 40. 40 is your optimized point. Let's erase this for more space. But we don't know if this is a local max or local min yet. So we can take the second derivative of this function. Second derivative of your first derivative. Okay, so S double prime is equal to 2 2 plus 256,000 divided by width cubed. Simply a derivative using power rule, and all we need to do is see what the value of the width is when it is 40. Well, we don't even need to evaluate this function. We can already tell that if we plug in 40 here, we get 40 cubed. That's going to be some positive number. And you're going to get 2 plus some positive number. That's literally just some positive number. So we know that the second derivative is some positive number when width is equal to 40. Therefore, we have a local min. Right? When the second derivative is positive, we have a local min. We have a local min at width equals 40, and that's exactly what we want because we want to minimize the surface area. So the width is equal to 40, but we don't know the height yet. So the height could just be calculated using this function. 32,000 is equal to height times width squared. Width squared is 1,600. Right, 40 squared is 1,600. And if we divide 32,000 by 1,600, you should get a height of 20. And since you use cubic centimeters, these are all the units will be centimeters in this case. So this problem will teach you future billionaires how to take advantage of the public. So let's go ahead and see this problem. A company estimates that if they price an item at $20, they will sell 500 units. And for every $1 increase in price, they will sell 25 fewer items. What price will maximize the revenue? Well, let's write a function for the profit. Let's use x as the amount of units. So profits is equal to units, amount of units sold times the price, correct? Well, units sold in this case is 500. I'm going to leave some space for what I'm talking about. And price is $20. Now, if they up the price by $1, so plus 1x, then they will sell 25 fewer items, minus 25x. So this relationship, this function here, kind of makes sense. Not kind of, it does make sense in the case of units times price. So for every dollar increase in this $20 price, you lose 25 people. And, oh, well, I kind of switched this around. P is here, people, units is the, oh, wait. Units is, oh, wait, no, I was right. Okay. I was right. As always, I was right. Okay, but in order to take the derivative of this, we need to, use FOIL. So let's go ahead and do some algebra. So profits, algebra, okay, let's write it here so I can save space. 500 times 20 is 10,000. You know what? I'm just going to pause the video. You guys probably know how to do this by now. So if you use FOIL, you just get this function for the profits. Okay, not profits. Revenue is the more right word. Oops. Okay, I've never taken an economics class. So revenues is the right word here. You won't make a profit. You won't make that much profit for that. But okay, let's go ahead and take the derivative of revenue. So the derivative of your revenue is, well, derivative of 10,000 is just 0. And the derivative of negative 25x squared is negative 50x. So the only time when the first derivative is equal to 0 is when x is also equal to 0. Therefore, if we use the second derivative test, we have a second derivative of negative 50. The second derivative is always negative, therefore we're always concave down. So that means x equals 0 is a local max. But wait, x equals 0 is just the first price, $20, 500 units. So that is a quite the coincidence that the optimization is already the answer given at the beginning. So yes, if you sell $20, 500 units, you would make the most profit to take advantage of your consumers. So as always, if you have any questions, put it down in the comment section. Thanks for watching.